So, amphiprotic, I talked about this a teeny tiny bit yesterday. Amphiprotic means that we have a species, which just means a compound, that can act, or an ion, either way, can act as both an acid and a base. Depending on the other things that are there, it could act as either an acid or a base. What was the one that we kept dealing with yesterday and today so far? Yeah, H2O, good. So water. Another one that we saw yesterday at the end of notes that we didn't quite have time to go through is the hydrogen sulfate ion, HSO4 1 negative, and a metal hydroxide. So we didn't quite get to that one yesterday, but I did say that would be a good one to do as some practice over the evening. And a lot of metal hydroxides. Now I have the Fresh Prince theme stuck in my head. Thanks a lot, Duncan. Okay, so the water, we can have a container of water. And on the particle level, most of it's just going to stay H2O. Most of the molecules are just going to be H2O. However, some of them will be in equilibrium with other water molecules with some acid and base forming. So one of my hydrogens says, see you later, water. I don't want to be with you anymore. Joining these guys. They say, right on. I like free stuff. Come on over. Join us. Okay, so the first one is acting as an acid. It's donating that hydrogen. It leaves us with an OH1 negative. So we're going to have some hydroxides in our big container of water. Now it's not noticeable enough for us to notice that we have any of those, but this is happening on the particle level. The other one that said, come on over, is now H3O1 positive, that hydronium ion that we talked about yesterday, which is acidic. So we have both basic and acidic ions in our solution. That's mostly just regular H2O. But on the particle level, some of this is happening and going back and forth. Most of it's going to be pretty instantaneous. They're going to hit each other in the right orientation, at the right amount of energy, and form the OH and the H3O positive, and then they'll go back. Okay. We talked earlier in this year about a guy named Lewis. Poor Lewis. We didn't talk at length about his history, but if you take the third semester of IB Chem and you choose to do the optional summer homework, you're going to read a little bit more about Lewis. Kind of a tragic life that he led. Some of it was his own fault. But kind of a tragic life. Didn't get the recognition for some of these things that he deserves. But we do name some things after him. For instance, Lewis structures. When we talked about Lewis structures, we were talking about bonding. What type of bonding were we talking about specifically when we were dealing with Lewis structures? No, really. Yeah, covalent. And it could be either pure covalent or polar covalent. So those ones that have an electronegativity difference between the molecules of less than 2. What if it's more than 2? What type of bond is that? Ionic, which means that we have ions forming. Those ions attract one another just through electrostatic forces, form some crystalline structures. But we're talking specifically about bonds being formed by sharing, either sharing equally, where the electronegativity difference is 0, they're sharing equally, or polar covalent, the electronegativity is somewhere between 0 and 2, they're sharing unequally. Sound kind of familiar? Some things we want to remember about Lewis structures. First of all, I have to look at where they are on the periodic table, because I need to know what about each of the species that I'm dealing with. The number of, valence electrons, good. So I'm going to need to know the number of valence electrons so that I can draw everything out. What is the rule for how many electrons most of the species need? What's that called? Octet rule, perfect. So the octet rule has to be followed. Each thing has to share 8 electrons, has to feel those 8 electrons, except for what species, what element? Hydrogen. How many does it need? Close. 2. Yep, it has one, it needs 2. Perfect. Good, good, good. So remember we do the octet check. What's the other check that we do for a compound after we've drawn it to make sure we've drawn it correctly? The octet check and why did I say we need to look at the periodic table? For the number of valence electrons. So what's my other check I have to do? Go ahead, Amira. If we then, which we'll look at that again later today as a little bit of a refresher. So we could look at the electron clouds and figure out what shape it forms. Yes, we could go that far. But even before that, Caleb? Beautiful. You need to make sure your check of the total number of electrons that matches up. Perfect.
But isn't that the, wait, is that rule? Or is that just having that there's 8 around every single one?
That there's 8 around every single one is the octet, and then the total electron check is making sure that you have double bonds where you need them as opposed to single bonds. Okay. Yep. Good. Okay, so that was our little refresher on Lewis structures, Lewis diagrams. Lewis becomes important for us for other reasons. So Lewis said, we know that a base accepts a proton. So a cation, a proton, the hydrogen ion, is going over to something else. It's going over to whatever our base is. Bless you. But the thing is, protons don't have electrons. Normally we think if we're forming new bonds, it's because there's electrons being involved. But protons, by definition, don't have electrons. So he said, what's going on here? We had our definition of Arrhenius. Arrhenius said that acids have to contain hydrogen and they donate that hydrogen in the form of a proton. Bases contain OH and it donates that as the form of hydroxide ions. We knew that wasn't right because of which compound? Ammonia. So Bronsted-Lowry came around and they broadened the definition a bit and they said, okay, an acid is a proton donor and a base is a proton acceptor. But that doesn't make sense here when we're talking about bonds being formed because electrons are being shared. So Lewis took that idea and this discrepancy and made our definition fit in a broader spectrum. So one thing that we learned when we were dealing with covalent bonds was that sometimes we can't draw them as nicely as we would think we could. Like carbon tetrahydride, CH4, we can put the carbon in the middle with 4 electrons around it, put a hydrogen on each 4 of those with a single bond in between each. Nice and normal for us. Not all of them are that normal. Some of them we do the magic and we start shifting electrons around a bit. And that is where we get these dative or coordinate covalent bonds, which you may remember from earlier this year, is an electron or both electrons that are being shared in a covalent bond are coming from one species. And specifically to acids and bases, the electrons shared come from the species that the proton is bonding to. So I have that H plus that's coming into something. The acid donates a hydrogen to a base. The base is taking 2 of its electrons and saying, here, let's share both of these. Rather than normally one will bring one, the other one will bring the other, so they're each bringing something. It's like a potluck. Everybody brings a little bit of something. Well, in a dative bond, the acid is donating that proton. Proton has nothing to give. And the base is saying, hey, no worries. Doesn't matter that you didn't bring anything. Here, have some of my food too. Okay, so the base is sharing both of those electrons. A dative bond, if you remember, is shown not with a single line, like we did with a single bond, or a double line for a double bond, or 3 lines for a triple bond, showing that 2 electrons, 4 electrons, and 6 electrons consecutively are being shared. But we show it with a line and an arrow. The arrow going to the species that is getting the electrons, the one that comes to the party with nothing. The arrow points at that one. So, in this instance, we have hydrogen iodide reacting with water, and I'm missing a couple of dots around here. Oops. So, iodine has 7 valence electrons. So there's the 6 on the outside. It is sharing one of its electrons with the hydrogen. Hydrogen also has one. So both of them are bringing something to the potluck. They're both sharing those. Water, again, I'm missing a couple of dots here. Water is going to say, hey, let's react. So the hydrogen from hydrogen iodide, or hydroiodic acid, if we're getting technical with the name, hydroiodic acid, it's going to donate that one hydrogen over here. So normally we would think of it that way, but it's not sharing anything. So we can think of it as, oops, get those 2 there. The oxygen says, hey, I've got this to share. Come on over, have some of my potato chips. So it shares its electrons with the hydrogen, breaking the bond between hydrogen and iodine. So we show it as sharing, but all of the sharing is coming from the oxygen and going to the hydrogen.
Then it's got an extra electron, and iodine is missing an electron.
Yes.
Because they have gone with the hydrogen.
Exactly. Good, good, good. And that's why we still have that +1 charge and the 1 negative charge. Perfect. Yeah.
Then does oxygen only have 6, or?
It is still sharing these 2, but it's sharing very unequally. So it's sharing, but the hydrogen isn't bringing any to the party. But it's still sharing, so it has 8. Good, good, good. What other questions before we move along? So let's look at the Lewis actual definition. We've talked about how he recognized that there was a problem and how he was able to say, well, I've been doing these things with Lewis structures. How can I relate that? Let's actually say what the definition is. So he said, let's broaden the definition. Let's make it work for more things. An acid is a species that accepts a pair of electrons to form a dative bond. Oh, frustrating. So we had that Bronsted-Lowry said that the base is the acceptor, which works as long as you remember that it is accepting a proton. The acid is accepting as well, which is where that gets us confused because we've got both a base and an acid accepting, depending on which definition we're dealing with. But they're accepting opposite things. The acid in Lewis is accepting a pair of electrons in the dative bond. Yep, Emily.
So it's like receiving electrons, but at the same time it's still like giving away one of its.
Exactly. So it works if we're dealing with stuff that has hydrogen. We could look at it both ways. We could look at it as both the Bronsted-Lowry and the Lewis way. But Lewis is, and we'll see this in 2 things here. We'll get there in a second. A base is a species that donates the electron pair to form the bond. But where we were getting with what Emily was just asking is that this idea allows the acids and bases to be extended beyond compounds containing hydrogen. So it's just flip opposite of the Bronsted-Lowry as long as there's a hydrogen there. It's doing the exact same thing. It's just that we're looking at the electrons, what those are doing, as opposed to what the protons are doing. as long as we have hydrogen. But Lewis was so innovative that he was able to say, hey, we have some things that are acidic, but they don't have hydrogen. So how can we define it more broadly? Question?
So if you're an equation and one side is with reactants don't have hydrogen bond.
Yes. Yep, perfect. Unless it specifically asks for you to use one or the other. Yeah. Okay, so here is a common example for us. It shows up in every textbook and everything online when you search for Lewis acids examples. So boron trifluoride. We know that boron is a small atom. It only has 5 protons. It only has electrons in the first and part of the second energy level. There's not a whole lot there. And so, it is satisfied, it's a satisfied compound, as boron trifluoride.
But it looks like it's missing 2 electrons.
It does look like it's missing 2. It does not fit the octet rule, but there are some elements when they're small like that don't need to fit the octet rule. We talked about that a little bit when we dealt with the Lewis acids or Lewis structures as well. There's a couple of oddball ones to memorize, and this was one of them. Well, when boron trifluoride, an acid, is near to ammonia, which we know is a base, they're going to react. And they're going to all react because of these 2 electrons there. Those 2 on the nitrogen. They're going to form what we call a complex, a big compound. So the boron trifluoride is in a covalent bond with the ammonia. They form a nice covalent bond. And we see with the arrow there that the nitrogen is the one that's sharing the electrons with the boron trifluoride to make the compound. Again, it's being shared overall, but the electrons that are being shared all come from nitrogen. Sometimes we see other elements that are in group 3 that can act as Lewis acids, just like boron is in group 3, so aluminum, gallium, indium, thallium, those all sometimes can form some of these Lewis acids. Now the thing that bothers me is that I can't find a good, clear explanation of how we would name this, nicely anyways, if it has a common name, and what it's good for other than being an example of a Lewis acid or Lewis base. So if you want some extra credit and you have some extra time, like 1 or 2 points, so it's not big, so just if you have extra time and you're on the computer, go ahead and look up what this complex, the BF3NH3, would be named and what it could be used for in real life rather than just a textbook example. That is all that I have for you guys today. I need some people to help me pass out papers, and there's a ton here, so maybe 4 or 5 people. Nikki, come on up. Who else? Excellent. Noah, come on up.